Now to Orlando from GrayMetal Labs.
Well, good morning. My name is Orlando MOREIRA. I'm the Chief Architect and Fellow at GrayMetal Labs. Today I'm going to talk about how to leverage sparsity to drive fast response times at the edge, of course, using our technology. So just a word about GrayMetal Labs. We are a global team. We are building SoC solutions for AI at the edge. We have 3 locations. One at Silicon Valley, where we have our product marketing and customer solutions. We are located in Paris too, where we have a science center and we do systems and applications engineering. And in Eindhoven, where I work, where we have our silicon design center, our architecture team, and where we also design the SDK for our platform. So what is the basis of our technology is a multi-core that we actually use to do scalable AI at the edge. The idea of the architecture is that we have a number of cores. Each one of these cores is an event processing pipeline that works on neuron pools. We designed the architecture explicitly to exploit sparse computation and dynamic scheduling of AI workloads by favoring in-place updates and relying on event-driven execution. So essentially, the neurons in the application, based on a kind of neuromorphic model, they reside in a specific core and they have a resilient state, and outputs of neurons are driven through the network on chip to a core where they are processed by the neurons in the next layer. We try to, so the architecture is based on having quite a lot of SRAM, where we can actually have all the weights, all the coefficients, and all the neurons residing locally in each one of the memories and not requiring external memory to lower power consumption. I said that I was going to talk about response time, and another way to look at it is talking about latency. Now, in edge applications, latency is very important. First, because we want to have responsive smart devices at the edge. Very often, these responsive smart devices are going to be part of closely coupled feedback loops. You have an environment that is constantly changing. You have to react to that environment, and you have to process whatever happened to your environment because of your own actions in the next, and so on and so on and so on. So it's not just a question of keeping up with the throughput. It's also a question of being very fast at replying to stimuli. And we're talking about autonomous systems. We want to actually have this intelligence residing locally in the device and not relying on a cloud service. Another thing that we see in most of these devices is that typically we are dealing with continuous data streams. The environment is constantly changing. We are sampling the environment either with a camera or with a microphone, with an industrial sensor ensemble, or even biosignal sensors. And this reply has to be kept going on continuously on an ever-changing and ever-present input stream. Now, I tried, of course, this is kind of a simplification of the whole question of latency, but to drive this discussion, I tried to define what we are interested in as what I call here response latency. So essentially, response latency is really the time that it takes between an event of interest happening in the environment around you and you finishing your edge device finishing the processing of such an event. There are two main components to this. There is the time that you actually take to process the event once you actually receive the data. That's what I call here the inference latency. So when your device gets the data, it starts churning on it, and at the end of a certain time, you get your response. That's inference latency. But there's another component that very often we think less about when we're talking about latency, which is actually the sampling latency. That is the time that it actually takes between the event happens and you can actually see it on your sensor. And this has to do with the sampling that your sensor does of the environment. So essentially, it's going to be the inverse of your sampling latency, of your FPS. Now, these two factors are pretty important. And an interesting remark here is that if you think about your sampling latency, it's actually, because it's the inverse of your FPS, it's going to actually be often dominating your actual response latency. And why? Because say that we have a device that can do the inference latency for a typical network that you need in the order of the tens of milliseconds. Our device actually for many networks makes less than that. But assuming that you do something in the tens of milliseconds, and if I plot for each FPS what kind of sampling latency you get, you actually see that you have to go to at least 120 FPS to actually be in the same ballpark. Meaning that very often it's your sampling latency that is going to dominate your response latency. Of course, we also want to keep the inference latency low, which means that we have to find the right balance between achieving a low inference latency and a high throughput. But bear in mind one thing, if you do conventional inference as we normally do, say that you have a stream of images coming in and you're processing every single one of them completely, you're going to actually, every time that you double your FPS to reduce your latency by half, you're actually doubling the amount of compute that you have to do. And this is something that we want to avoid. Now, at GrayMetal Labs, what we do is that essentially we are looking at two factors that we think are keys to low latency at the edge. One of them is doing event-based self-time scheduling of your compute. The other one is exploit sparsity in your input data. I'm going to talk a little bit about each one of them. Necessarily, there's going to be a simplified discussion because of the amount of time I have. But just to give you an idea, if you want to discuss this, then you can come to our breakout session afterwards. Essentially, one way that AI is processed very often is by doing single batch processing. How does that work? Typically, what you do is that every time that one of your frames comes, you actually start allocating all the compute resources of your device to do the first part of that frame, typically process layer 1, then process layer 2, then process layer 3, layer 4, and so on. It is a way of scheduling that actually makes it pretty easy to synchronize, because actually you have few synchronization points. It also helps you with actually having fewer context switches, because you have to load new state when you get your new weights in the next route. So you actually want to reduce the amount of times that you do this. And it does give you a very low latency, but because it doesn't allow you to flexibly assign your resources where you need it the most, it essentially, or to start working on other work before, it tends to favor low latency over high throughput. So it's a very good way to work if you want a very low latency. It doesn't work so well for throughput because you cannot start working in the next frame if it arrives early. Essentially, it concentrates all your resources in one thing. One way that is typically done in edge devices to actually get high throughput is actually doing the opposite. You tend to allocate your resources, reserve your resources for a particular stage of the processing. That means that you don't have any context switching whatsoever, because each one of these resources is allocated to doing that. So for instance, all your weights are residing in the device, because the device always uses the same weights. It creates a form of locality of reference. And then each one of the resources does one part of the compute, so it gets one stage of the execution. Grosso modo here, I assume that I would map that to layers, but sometimes you can, of course, merge layers and so on. And then what you do is that each one of them does its thing, and then you are allowed, typically this allows you to get higher throughputs, but the cost that you get for this is latency, because now you have a very strict way of executing that first you have to be done with one before you pass to the other, and so on. So typically this gives you high throughput, but it comes at the cost of typically a high latency. Now, and it does have still a relatively simplified synchronization, because you only need to actually schedule the transfer of data between stages. Now, one thing that you would want to do, but it is typically more difficult to synchronize, is that actually you want to do pipelining, but you want to do it in such a way that you can start immediately working on the second layer before you're actually done with the first, because this allows you to actually get a much lower latency and still have the sort of resource allocation that will allow you to get a high throughput. Now, the way to actually manage to get to this is that you need, rather in many architectures, you would require a very intricate type of synchronization to actually allow for all of these blocks to communicate with each other while having limited buffer sizing between them. One of the great things about our architecture is because it's based on self-timed execution and event-based execution, that you actually, the moment it is fully data flow based, meaning when I get an output, I send it to the next core that has to process it, and the arrival of the data to a free resource actually causes the execution to start. So in that sense, our architecture is particularly good at doing this type of striped or mini pipeline execution. So our NeuronFlow architecture, because it's event-based, it's naturally designed to leverage this mini pipelining or striping. We have near memory compute that keeps the weights and feature maps local to the core, so there's no context switching. Each device is concentrated on a single set of layers that is going to execute. And because we have event-based processing and push execution model, meaning that the producer sends the data and the arrival of the data causes the computation to start, it simplifies self-time synchronization and allows us also to exploit what I'm going to explain in the second part, which is sparse execution. So one thing is that we can do a good, with event-based execution, we can do a pretty good trade-off between reducing our inference latency and getting a low sampling latency. But the problem still is what I mentioned in the beginning. In a traditional execution where we execute frame by frame, we are going to have that high frames per second. So low sampling latency requires high frames per second. High frames per second is going to require high compute load because you're just multiplying by factors the number of frames that you have to process. So the question is, can we boost our frames per second while avoiding increasing the computation requirements? And that's where sparsity becomes the key characteristic. So to think about what sparsity is, essentially it's the fact that when you look at any data that you get from the environment, there's a lot of redundancy or non-interesting data or information in that. Data in what you receive. We already know that we can exploit sparsity in structure, which really means that you pull needless weights from the network and kernels because you're not really using them. That's kind of the other side of sparsity that resides at the network. If you think at the sparsity that you have from the side of the data that you receive, you have sparsity in space. In a very large part of your image, there are no features of interest. In our architecture, because of the data flow concept, all of this results in zero-valued activations of your neurons that don't send any data to be processed, so they just are completely skipped to the point that there's no sending of data, there's no reading of memory, nothing. But there's also another type of sparsity that most architectures cannot exploit, which is sparsity in time. This is the realization. I have here a frame of somebody biking, and then you see the second frame. The second image is the difference between two frames in a video sequence. What this tells you is that from the first image to the second one, almost nothing changed. Yet, if we do the typical processing that we do frame by frame, we are going to have to reprocess the whole image to actually understand it. Now, there's no point in reprocessing the whole frame. That's the point that we try to make, but we have to be smart about how do we do this, and we have to do it in real time. But if we can do it, then processing more frames is not going to cost us as much. So the idea that I want to put here, and that is one of the key concepts in NeuronFlow, is that what we do is that instead of processing always a full frame, what we do is that we only process a full frame the first time around, like when we start execution or every now and then when the scene changes. And then from then on, we only look at the change of what has happened in the sensor. We receive this change and we only process the change. So essentially what we do is we execute standard networks. So we're talking here about mobile nets, res nets, YOLOs, what have you. But we are processing them in a way that we turn them into a network that processes a first frame and then difference frames, so to say. What happens is that what we get is that instead of having to process the whole data of the frame through the network, we keep resilient state for each one of the neurons, but then we only process whatever changed in the frame. And this should reduce a lot the amount of computations that we have to do. And if it reduces the amount of computations that we have to do, it's also going to have an impact on our inference latency. But it goes beyond that, because if we do it right, we actually don't just affect our inference latency. Before that, I forgot I was going into the next slide. I'll show you an example of how much, if you do the inference frames, if you do the data frames, the frames that only look at what changed from the previous one, the reduction in the amount of computation that you have to do. So here you have a scene where you have a car driving, and we're running a network called PilotNet. And here we are processing frame by frame. Here we are processing only what changed in the frame. And you can see here in blue the amount of computation that we do when we're processing what changed in the frame, compared with the red line, which is processing the full frame. Now, what you see is that typically we have a lot less to process, because from one frame to the other, very little changes in the environment. Once in a while, we have spikes when there's a lot of change in the environment suddenly. But most of the time, we are going to actually process a lot less if we do our incremental processing instead of the typical frame-by-frame process. So the point I wanted to make here now about frames per second is this. If I increase my frames per second and I do frame-by-frame processing, what I'm going to do is that as I increase the number of frames, I linearly increase the amount of processing that I need to do. That's just obvious, right? I'm just processing more. However, if instead of that you use our delta frames, actually your amount of processing is going to kind of plateau. Why? This is very easy to explain. It's because in the same amount of time, doesn't matter how many frames I do, the amount of change is more or less, it's not completely constant, because there's a bit of a noise here and there, but it's mostly constant. There's a lot of, put it like this, if I sample it at 480 or 30, not more stuff is going to happen during that amount of time. So I'm going to actually reduce by a lot, dramatically, the amount of processing that I have to do, because within a time interval, I have a fixed amount of change occurring in the system. So what NeuronFlow will allow you to do with our time sparse inference is that you can increase very modestly this load with the FPS, but you're going to get all the advantages of the lowered response time that you get from increasing the FPS. So essentially, we can double the attainable sampling frequency with a negligible increase in computational requirements, while before we were settled with actually doing this just linearly. We have made a chip to test and prove these concepts. We have our GrayOne chip that it's still very small, so we were still, to an extent, we were learning how to pack so much state in a chip. So it only really has 200,000 neurons for 20 square millimeters. It is, however, fully programmable in TensorFlow. It doesn't use any external RAM, so it keeps the whole network inside of itself. In the meanwhile, we actually have made quite some breakthroughs in actually allowing for a much higher number of neurons to fit in the same area. So I hope you'll hear about it very soon. But with this demonstrator, what we did, we ran a pilot net on it. It had to be a relatively small network. And the result was that we measured the latency when we do full frame execution and compared it what we do when we use our sparse frame with essentially the same accuracy. And what you see is that we actually went from, when processing full frames, having a latency of 40 milliseconds and reducing this latency to 2 milliseconds per frame. And this is talking only about the inference latency side. Of course, there are also very many gains that you can get just by increasing the frequency. And indeed, we could increase the frequency by a lot. I think I have to get done. So to summarize, the NeuronFlow architecture addresses response latency at the edge. It does this by tackling both sampling latency and inference latency. High FPS without linear increase in computation energy requirements addresses sampling latency. We can get, through exploitation of temporal, spatial, and structural sparsity, we can get very high sampling rates without increasing the amount of compute. And on the other side, the usage of mini pipelining, which is allowed by data flow synchronization. So as soon as possible, self-time push synchronization. We can get low latency without sacrificing our throughput. And the sparse temporal execution also reduces the computations that we do per frame and allows a faster computation, therefore also reducing inference latency. That pretty much concludes my talk.
Great. Thank you, Orlando. That was very, very impressive.
Again, just a quick shout out to our sponsors. Bear with me for 1 minute. We have different categories. We have executive sponsors. First one being ARM. Then we have Qualcomm. We have Samsung. Platinum sponsors. ADA Compute. Lattice Semiconductor. Gold sponsors. BrainChip. Babel Labs. DSP Group. Edge Impulse. EMSA. GrayMetal Labs. Greenwaves. Himax. Imagimob. Latent AI. Maxim Integrated. Quixo. Reality AI. tinyML. Silicon Labs. Sentient. Google TensorFlow. XMOS. And lastly, silver sponsors, Edge Cortex, Hotchi, and Synsense.